repaired like that, isn't it, sir?
Yeah, yeah.
One four
The thing is,
two
it's,
here.
you're right. So let me tell you, not that it is not possible, but these are random events because we are looking at post outage rate. So it's not a planned shutdown. So it's kind of, breakdown, reactive. And therefore, two units failing simultaneously, not that it is not possible, but the probabilities are going to be very, very low of the occurrence of that state. So the probability is so negligible that any multiplication with any terms would not make any difference. So that's the logic, mathematical logic, why we do not consider simultaneous failures of two or more units, more than one unit.
At the same time, we can repair also 2 units simultaneously. Is
Yeah,
it
yeah.
possible?
So again, those probabilities are going to be very, very low. Simultaneous repairs.
Okay, thank you, sir. Thank you.
So simultaneous failures and simultaneous repairs. So at a time, we consider a single failure and a single repair. Not that it's not possible, but the probabilities are so low that they would become inconsequential. Mathematically, they would not make any difference. So, okay. So 40 to 0. So from 1, 4 to 1, 2, 3, 4. Then probability of 1, 4, probability of 2, 4, probability of 3, 4, probability of 1, 2, 3. So 1, 4 to 1, 2, 3, 4, 2, 4 to 1, 2, 3, 4, 3, 4 to 1, 2, 3, 4, 1, 2, 3 to 1, 2, 3, 4. And the sum of these probabilities. So let's look at this. 1, 4 to 1, 2, 3, 4. Is that possible? So that would mean simultaneous failures of two of them, 2 and 3. Then 2, 4 to 1, 2, 3, 4. So that's not possible. Simultaneous failure of 1 and 3. Then you have 1, 2, 3, 4. From 3, 4 to 1, 2, 3, 4, simultaneous failures of 1 and 2. That's not possible. So from 1, 2, 3 to 1, 2, 3, 4, yes, single unit failure. So 4 can fail and it could take you to this state. So that's lambda. So you just are left with, so these are zeros, these transition rates are zeros, and this is just lambda. So P1, 2, 3 into lambda. So lambda is 0.4, and then P1, 2, 3 is this probability. Okay. So you can see here 1, 1, 4, 1, 2, 4, and 3, 4, these probabilities are same. So 3 into this and plus probability of 1, 2, 3, which is 6.144, which is the same probability which is used here in this calculation. So in the numerator, you have the failure rate in the last term and the probability of 1, 2, 3 failure. So that's 6.144. Here also 6.144. So you get 40 to 0. This is the transition rate. Now let's look at 0 to 40. 0 to 40, there is only one state. This is merge state. So this is the merge state which we have to look into. So transition from 1, 2, 3, 4 to 1, 4, 1, 2, 3, 4 to 2, 4, probability transition from 1, 2, 3, 4 to 3, 4, JI, okay, capital J to K, capital I. So 1, 2, 3, 4 to 1, 2, 3, and this probability is same, from everywhere. All the 4 states when it is migrating, because it's already just one state. So, so it would appear in the numerator as well as in the denominator, just one state. So multiplication of state probabilities is same. So let's look at this term, 1, 2, 3, 4 to 1, 4, 1, 2, 3, 4 to 2, 4, 1, 2, 3, 4 into 3, 4, 1, 2, 3, 4 into 1, 2, 3. So that's, these terms would simply disappear because they are not possible. This would mean 2, 3 failing simultaneously. This would mean 1 and 3 failing simultaneously. This would mean 1 and 2 failing simultaneously. This simply means 3 getting 4 getting repaired. Okay, 4 getting repaired here. So single repairs are possible. So this is mu. So, and you are multiplying with the same probabilities everywhere and then dividing by the same probability because there is just one state. So multiply by the state probability each of this term and divide by that same probability. of that state. So all of them disappear. So you're just left with mu, which is 9.6. So we have been able to deal with 40 to 0 and 0 to 40. Now we are simply left with 20 and 0 and 0 to 20. So let me take you back again. You know, all the time we keep referring to that diagram so as to keep your focus and to keep relevance of what we are doing, you know, because every time you look at it, you know what's happening. So 100 to 80, 80 to 100 is done, 80 to 60, 60 to 80 is done, 100 to 60, 60 to 100, 80 to 40, 40 to 80, 60 to 40, 40 to 60, 40 to 20, 20 to 40 is done. So now we are going to see 40 to 0 and 0 to 40, I think, and 20 to 0, 0 to 20. So I think just two states are left, if I recall correctly. "40 to 0 and 0 to 40. Did we do this? Yeah, we have done this. 40 to 0 and 0 to 40 we have done. Now we look into 20 to 0 and 0 to 20. So 20 is, you know, states where unit 4 failure is involved. So 40, 20, 20. So that's 80 megawatt down. Here also 80 megawatt down, 80 megawatt down. So the state capacity is 20 megawatt. And here all of them are down, 0 megawatt. Nothing is remaining. All of them are down. So we want to merge these states and then find out from 20 to 0 and 0 to 20. So this makes life easier. There aren't too many. So from 1 to 4 to 1 to 3, 4, 1, 3, 4 to 1, 2, 3, 4, 2, 3, 4 to 1, 2, 3. So 1, 2, 4 for transition rate from 1 to 4 to 1, 2, 3, 4. Then 1, 3, 4 to 1, 2, 3, 4. Then 2, 3, 4 to 1, 3, 4, 2, 3, 4. And some of these probabilities. State probability. Okay. So 1, 2, 4 to 1, 2, 3, 4, yes. Unit 3 fails. That is single failure. 1, 3, 4 to 1, 2, 3, 4, yes, that's possible. 2 fails, single unit failure. 2, 3, 4 to 1, 3, 4, yes, 1 fails, that's failure rate, and that's single failure. So there is failure rate, lambda here, lambda here, lambda here. And these probabilities are same, you know, 1, 2, 4, 1, 3, 4, and 2, 3, 4. These probabilities are same. And anyway, lambda turns out to be common. And then in the denominator also, you have the same term. And therefore, they cancel out. You are simply left with lambda, which is equal to 0.4 per year. So this is 20 to 0, and then 0 to 20. This is then 0 to 20. What is 0 to 20? From 1, 2, 3, 4 to 1, 2, 4, 1, 2, 3, 4 to 1, 3, 4, and then 1, 2, 3, 4 to 2, 3, 4. And then, of course, the probability in the numerator and the denominator, it's just one state. So the multiplication product with the same probabilities is there. So 1, 2, 3, 4 to 1, 2, 4, 1, 2, 3, 4 to 1, 3, 4, and 1, 2, 3, 4 to 2, 3, 4, multiplied by P divided by P. So 1, 2, 3, 4 to 1, 2, 4, yes, possible. 3 can get repaired, so mu. 1, 2, 3, 4 to 1, 3, 4, 2 can get repaired, so that's mu. 1, 2, 3, 4 to 2, 3, 4, 1 can get repaired, so that's mu. So that's equal to 3 mu. I think the terms are slightly looking misplaced, but that's 3 mu, so that's 28.8 per year. So now we have the transition rate from lambda 20 to 0 and 0 to 20. Okay, so now we have found out all the state probabilities and the transition rates. Now we are in a position to develop this capacity outage probability table. Okay, so here you have, you know, because you know all the departure rates. You have the departure, you have now the various states from 0, 20, 40, 60, 80. These are the states of the system. You know, you remember we saw that converged model. Zero, 20, 40, 60, 80, 100. So in the capacity outage probability table, we take you back to the okay, so 0, 20, 40, 60, 80. So these are the number of, here nothing is out, here 1 unit is out, here 2 units, it could be, or it could be 1 unit, you know, 40 megawatt or 220 megawatt. So those combinations and mergers have already happened. And these are the state probabilities which we have already calculated earlier. And these are the cumulative probabilities. Cumulative probabilities, that means, say, having capacity up to 20. It could be either 0 or 20. So that's cumulative probability. Okay. Then from 0 to 40. So that's a cumulative probability. Then from 0 to 60, that's a cumulative probability. You know, this star refers to cumulative probability. Then 0 to 80. So that's the cumulative. So we are simply adding up these two terms. If we add this, the last and the second last, it gives you this in the table, in the cumulative. If you add up these individual 0 and 20 state probabilities, it gives you the cumulative up to 20, then up to 40, then up to 60, then up to 80, and of course up to 100. That means the probability will be 1. And then from 100, departure to a higher capacity state, which is none. Nothing is higher than 100 here, because the maximum capacity is 100, so 0. And then to a lower state, that's 80. That's 80. Okay, so 100 to 80, 100 to 80, departure to a lower state. But 100 to 80, if 20 unit fails, if 40 unit fails, it goes to 60. So the departure rate, you know, there are 2 departures to lower state. One is to 80 and one is to 60. So you refer back to those transition rates where we found 100 to 80, 80 to 100, 100 to 60, 60 to 100. So when you are referring to departure to lower capacity state than 100, so you look at 2 possibilities, 100 to 80 and 100 to 60. So you find these 2 departure rates and you sum them up. Departure to lower capacity state becomes 1.6. Likewise, from 80, departure to where can you depart to a higher state? It's just 100. So that means if there is some repair, then you move to 100. There is no other state to which you can go to a higher state. So that's the repair rate, which we had also found out using those analysis and calculation, which we have seen earlier. So this is, you know, departure to higher state from 80 to 100. So that's 9.6. And to a lower means it could be 80 to 60 or it could be 80 to 40. Remember, 80 to 60 is 20 unit failure, or if 40 megawatt fails, then you go to 40. So there are 2 departures to lower state possible, and therefore 80 to 60 and then 80 to 40. So departure to lower capacity state, sum them up, you get this. Then from 60, you want departure to higher state. It is possible to go to 80 or it is possible to go to 100. So you take the transition from 60 to 80 and 60 to 100. So departure to higher capacity state, you add them. Then from departure to lower capacity state, either from 60 you can go to 40 or you can go to 20. So you take these 2 departure rates and then you add them up. So that gives you departure to lower capacity state. Then you come to 40. From 40 you can go to, you know, you can go to 60 or you can go to 80. You know, if higher state. 40 you can't go to 100 because if the unit which is 20 megawatt that gets repaired, will go to 60. If 40 megawatt gets repaired, you'll go to 80. Okay, and so you have two departure rates, 40 to 60 and 40 to 80, and you add them. And then lower, you can go from 40 to 20 if 20 megawatt unit has failed, or 40 to 0 if 40 megawatt unit has failed. So you add them up, and that gives you departure to lower capacity. Then from 20, you can go either to 40 or you can go to 60. That means a higher state. If 20 unit has got repaired, you'll go to 40. If 40 unit has got repaired, you'll go to 60. So you have two of them. Okay, two of them, and you add them up and you get. So you can find out these transition rates from the calculations that we have already done. And lower from 20, you can only go to 0. So that's already single unit. So that means if it fails, you'll go to lower. You will go to 0. Therefore, that's 0.4. Now from 0, you can go to 20 or you can go to 40. So you have, it can go to 20 or you can go to 40. You can go to 20, that means some single unit repair. And 40 means either it's a question of 20 units or it's a question of 1. So anyway, so you can refer back to the analysis that we have done earlier. So there are two possibilities and therefore two transition rates, and you sum them. And then departure to lower capacity state is not possible from 0. So you have nothing. So now you have departure rate to higher capacity state, departure rate to lower capacity state. Okay. So now you are interested in finding out the cumulative frequencies. Okay. So what we are doing is the cumulative, the frequency is, how do you calculate this frequency? You add up these departure rates. You remember some expressions that we had arrived at regarding frequency, the relationship between the departure rate and the probability and the frequency. I must take you back, very far back. Yeah, okay. You see, frequency is sum of the departure rates. Sum of the departure rates multiplied by the state probability. The frequency of encountering state I is the probability of being in state I multiplied by the sum of the departure rates. Okay, so that's what it is. And therefore, we are trying to find out the frequency of encountering these states. Okay, we are yeah. So we are trying to find out the frequency of encountering this state. So for example, here we would simply, this is a cumulative probability, of course. So what we are doing is the sum of the departure rates, not just the higher or the lower state, but some of these two departure rates, either to the higher or to the lower. So 38.4 plus 0 is 38.4 multiplied by this probability, that would give you. So this is the state probability, 38.4 and 0. You saw 38.4 and 0. So lambda j plus lambda j minus. So that's 38.4 multiplied by the state probability. So that gives you the cumulative frequency of encountering state 0. I mean, if you just took individual frequency, that means at this stage where you are looking at a state where you have 0, where you have 0 megawatt, that's okay, whether you call it individual frequencies or simple frequencies or cumulative frequency. Now let's look at 20. So that means either 0 or 20, So you have these cumulative frequencies. So you find out this probability, do you remember? So what is the state probability and the cumulative probability? 0.000186888. And the individual probabilities are 0.0001843.432. So you have taken 0.0001843.2, and what are these transition rates? 28.4 and 0.4. Okay, so that's 28.8 and 0.4. So that gives you this. Likewise, for state with 40 megawatt capacity, so you look at these probabilities, 0.00448512, and then you look at these two, and then you have, yeah, so you have these terms, okay, lambda j plus and lambda j minus. So for some reason, this is called cumulative frequency, okay. So then you have states with 60 megawatt. So 60 megawatt, the probability is 0.03981312, and these are the two departure rates, 10.666, 1.555. So you have 0.039, this is the probability, and 10.666, and the departure to a lower state is 1.555. So this gives you the frequency of encountering this state. Likewise, frequency of encountering state 80. So you have this probability, and then these are the two departure rates. So you have 0.106, 9.6 plus 1.2. So that gives you the frequency of encountering state 80. Frequency of encountering 100. So you have, you know, there is no higher state, so that's 0, and this is 1.6. So 0.16, and then this is the probability. So this is the cumulative frequencies, as they are called. Okay, so what we have been able to do is we have been able to find out the state probabilities and the frequency of encountering these states. Frequency of encountering these states. So that's quite important, you know. What will be the number of times you'll encounter, say, 60, or say 40, or say 20, or 80, you know. So that's the frequency. So you have frequency of encountering and the state probabilities. So that's the table for cumulative frequencies. So next we'll go over to LOLP and expected energy not served, you know, some indices. Okay, so LOLP. LOLP is defined as the probability of generating capacity being less than the daily peak load over a given space of time. So yeah, generating some amount, and then there is a demand, there is a peak load. You know, whenever there is a peak load, then the generating capacity falls short of that peak load, so that load will be lost. So that's loss of load. Loss of load. What is the chance of losing load when you say when there is a peak load, especially peak load? Okay, so that means the load is greater than the capacity, and what is the probability of getting a capacity. So when you have different capacity states, you have seen that you have different capacity states. Although you may have 4 units cumulatively giving you up to 100, but you have different capacity states depending upon which gets which fails and which gets repaired. So you have different capacity states, and therefore probabilities associated with those capacity states, and therefore there is some load which is there is some load, there is a demand, there is a load, or say it could be a peak load which is greater than the capacity. So the balance of that load will be lost, and therefore what is the loss of load probability? It is one way to look at it, or you take the probability of occurrence of a load and the capacity becomes less than the load. If the capacity is less than the load, then the balance is lost. Then the balance which is over the capacity and the load, that's lost. Okay, so we need to find out this loss of load probability. What is the chance of losing load? Okay, so this is, let's say, installed capacity, and let's say this is the peak load. Okay, this is the peak load. So this is of course the reserve that we have. This is a peak load, and over and above there is some reserve. So that's the installed capacity. And because of certain outages that happen, your installed capacity reduces to a certain level. You don't know whether 40 megawatt is lost, or 20 is lost, or 60 is lost, or 80 is lost. So it will reduce. And when you reduce, then obviously the load which is above the state capacity current, that load will be lost. So that means for the percent of time for which the load is above the capacity state, that will be lost. So capacity outage state of, so if this is the installed capacity and this is the outage, that means you are going to lose this much of load over, which will exist over a certain percentage of time, the affected duration. So mathematically, we say that the loss of load expectation is sum of the PK. PK is the probability that the peak load will not be met, multiplied by the time period for which the given peak load exists. You know, the peak load which is not being met, you know, the probability is this, and the percentage of time for which it will not be met, for which a given peak load exists, is this. And therefore, when you sum up all of them, why we are saying K? Because the capacity states can vary. You know, the state capacities can vary depending upon what happens, depending upon failures. Therefore, although installed capacity may be something, but there can be an issue with failures, and therefore your current capacities can be less. And so you take these probabilities of loads, peak load will not be met, probability that the peak load will not be met, obtained from the generation model, and time period for which a given peak load exists, obtained from the load model. So you have load model, you have a generation model, and then you combine the two, and then that gives you loss of load expectation. Loss of load expectation. So loss of load expectation is primarily probability of a capacity outage state, percentage of time this outage can cause a loss of load. Okay. So let's look at a couple of examples that could make things a little more clear. So you have a generation profile of 3 units of 20 megawatt each, and the same problem that we looked at. Okay, and 1 unit of 40 megawatt each. You know, we have handled the same problem. We found out those transition rates and frequencies and those state probabilities in the previous capacity outage probability table. So this is the generation profile. Let's look at the load profile. 5% of days during which a given period of observation, the peak load is between 30 and 40, 15% between 40 and 50, for 30% between 50 and 60, and for 30% between 40 and 50, and for 20% between 70 and 80. You can add them up and see if that's 100. So 5%, 15%, that's 20%. This 30%, 50%, then that's 80%, 20%. So 100%. Okay, so load profile, you have load profile. So we need to find out the loss of load probability. So between 30 to 40 megawatt, 5% of the time. Then 40 to 50, 15%. 50 to 60, 30%. 60 to 70, 30%. And 70 to 80, 20%. Okay, so you have say 20% of the time you have a load which is 20% of the time it's between 70 and 80. Then 60. Then between 60 to 80, it's not 60 to 70. Another typo here. 60 to 80, it's 50% of the time. Then 50 to 80. So that's 30, 30 and 20, 80% of the time. Then 40 to 80, it's 95% of the time. Then 30 to 80, it's 100% of the time. This is not 70, 60, 50 and 40. That's all 80. So this is the load profile, cumulative load states. So load duration curve for the given load profile. So this is what it is, more than 80, 0% of the time. So between 80 to 70, it's 20% of the time. This is 70. So this is 20% of the time. Then you have between 60 to 70, it's 30% of the time. This is 20 and this is 50. And between 80 to 60, it's 50% of the time. You see, 80 and 60. From 80 to 60, that's 50% of the time. Then 80 to 50, it's 80% of the time. 80 to 40, it's 90%, 95%. And then between 30 to 80, it's 100% of the time. So this is the load profile, and this is the installed capacity. Okay, so you have the load and you have the generation, and you want to find out, because of the varying, because of the varying states of the generation, and because the percentage of time for which the load also keeps varying, the generation also keeps varying, and therefore the two together, what is the chance that load will be lost? Okay, so you have COPT for the generation profile that we already know. This is what is already known, and then percentage of time the outage capacity will cause loss of load. So let's look at this. So if there is capacity is 100, and if 100 is available, is there any loss of load? No. So 100, capacity out is 0. So therefore percentage of time the capacity will cause loss of load is 0. And then capacity is 80. So capacity out is 20. So anyway, the load varies between 30 to 80, and there is no load above 80. So percentage of time for which the load will be lost is 0. Then since the load varies up to 80, so 62, if the capacity is 60, so any load between 60 to 80 will cause a loss of the load. So what is that percentage of time, 60 to 80? Yeah. 60 to 80, 60 to 80, yeah, 60 to 80, that's 50% of the time. So from 60 to 80, 50% of the time. Then 40 to 80, what is the percentage of time for which the load will be lost? 40 to 80, 95% of the time. Okay, 40 to 80, 95% of the time. And then 20 to 80 is 100, because the load is not lower than 30. So if you have states with 20, if you have states with 20, then you have 100% of the time the load will be lost. And if you have state with 0, 100% of the time the load will be lost. So percentage of time the outage capacity will cause loss of load. So this is the table. Now we need to find out what will be the loss of load probability. So you need to take the probabilities and multiply. You remember this expression? Either of the two, if you know the probabilities of the capacities, state capacities, or the load being more than the capacity, percentages of time, or the percentages of time, and then these possibilities of load. Okay, so you have 0, 0, of course. Then you have 50%. And what is the probability of getting a state 60? So that's 0.0398131. okay, and then 95%. So you have 95. So then probability of getting this state 40 with 60 out. 60 out. So let's look at this. So this is 60 out, 0.448512. You remember? 0.448512. This is a probability, and this is 95%. So the two get multiplied. And then probability of getting state 20, 0.001842. And then 100% of the time. And then probability of getting 0 is this, and then that's also 100% of the time. So if you add all of them up, the product of these percentages of time for which the load lasts and the probabilities of those states, you get the loss of load probability. So the loss of load probability is this. So that's in a year. So per year. So if you multiply it by 365 days, so you'll get days per year. So 8.889. So approximately 8.9 days per year. The loss of load expectation. This is the LOLP. Loss of load expected number of days over a year is so much. LOLE, you simply multiply it by 365 and you get the number of days in a year in which there will be loss of load. Okay, the capacity which is available will not be able to meet the load which is there. So if you have the load profile and you have the generation profile, then you can find out the loss of load probability, loss of load expectation. Now these numbers may not mean much, but when you multiply it by 365, it tells you the days in a year approximately for which the load will not be met. Next is what you have is expected amount of energy not supplied during some long period of observation to the total energy required during the same period. Now this is yet another index, expected amount of energy not supplied, because it means revenue, of course. During some long period for a certain facility or utility, it means revenue. So therefore, these indices are handy to calculate and to use. Expected amount of energy not supplied during some long period of observation to the total energy required during the same period. Okay, so this is the installed capacity, this is the outage, and then this is the load profile. So if this is the outage, then this is the duration for which the load requirement will not be met. This is the percentage of time. So you want to calculate the energy, all you need to do is to integrate and find out this area. Integrate and find out this area under the load profile. So that's not a big deal. So, and expected energy not served, you know. So what we have done is we have integrated this DJ with the probabilities of the state probabilities and sum them up and then divided it by the duration. So expected energy not served, you know, and DJ is of course this is the load profile L, and the total duration of course is simply the integration of load and the time. So that's D. So anyway, D is not an issue, but trying to calculate this is an issue. So for different states of the system, generating states of the system, what is the duration for which it will be lost? So that you need to find out, multiply by the state probabilities, and of course divided by the duration, which could be 1 year or per year, whatever, and then you get it. And then you get the expected energy not served. So let's look at the same problem that we addressed earlier. 3 units is not 30 megawatt each. let's say it's 20 megawatt. I think there's a typo here. One unit is 40 megawatt each. The outage rate is same. So this is 3 units, 20 megawatt each. The same problem that we took earlier. The same problem, because we already have calculated the probabilities. So there is little point in taking up another problem. So let's say 20 megawatt each, 3 units, 1 unit 40 megawatt. The outage rate is different. And this is the load profile. 30 peak load, 35 megawatt, 5%, 45 megawatt, 15%, 55 megawatt, 30%, 65 megawatt, 30%, 75 megawatt, 20%. So let's take the generation profile. And of course, you already have the load profile, it is there. You can also show it in some other ways also, but it's already there. So all we need is the generation profile, which we already have ready. We know the state probabilities, we know these cumulative probabilities. So this is what is required, and the load profile is required, and the two have to be convolved together. So what is the probability of the load? 35, 5%, 45 megawatt, the peak load, 15%, 55 megawatt, 30%, 65 megawatt, 30%, 75 megawatt, 20%. So this is 80%, 95%, and 100%. And so the probability that the capacity is less than the load. So this is 35. So the generating state can exist in 0 megawatt, 20 megawatt, 40 megawatt, 60 megawatt, 80 megawatt state, and 100 megawatt. So the probability that it can exist in less than 35 megawatts, less than 35 megawatt, that means in these states you will lose the load, 0 and 20. So you have this probability and you have this probability. So if you have to look at both these two states, then this is the collective, cumulative probability. This is how the cumulative probability can come in. So probability that the capacity is less than the load, when you are in state 0 and 20, you will lose. So therefore, the cumulative probability is 0.0001868. So the capacity less than the load, so you will lose. Okay. And then you multiply this, so you get a probability of the load. This is 5% of the time. So 0.05 multiplied by this, you get this. Then let's look at 45 megawatt. So what are the states in which you lose the load? When you are in 0, 20, 40, you lose the load. 0, 20, 40. So what is the cumulative probability? Each of them added up here. So cumulative probability is 0.004672. So 0.004672 multiplied by 0.015. And therefore, you multiply these two numbers together and you get, this is PL multiplied by capacity less than the load. So in 45 megawatt load, you have states of 0, 20, 40 where you will lose the load. So this is the probability to look for, and multiplied by the percentage of time, and so that gives you the gives you the loss of load probability when you have 45 megawatt. Likewise, when you have 55 megawatt, what are the states which can cause loss of load? When you are in 0, 20, 40. So the cumulatively it's 0.004672. So again, this is 0.004672 multiplied by 0.3. So that gives you the loss of load probability when you have 55. Likewise, when you have 65, then all these 4 states can lead to a loss of load. So you take this cumulative probability, 0.4448512. So you have 0.4448512, 65, and this is the percentage of time for which it lasts. So this gives you the loss of load probability when there is 65 megawatt. Let's look at 75 megawatt. So when there is 75, then 60, 40, 20, 0, this will again can cause a loss of load. So that's same probability, the cumulative probability 0.0008, 0.04448512. So 4448512. This lasts for 20% of the time. So this is it. So if this could be the load profile, either of them could occur. And of course, the capacities can lead to loss of load. So these are the LOLP corresponding to these peak loads. So if any of these states can occur, then this would be accumulative. You add up all these numbers, so you get 0.0243 and multiply it by 365. So you get these 8.4289 days per year. You know, this number of days per year loss of load probability. But you want to find out the expected energy, not served. You know, so we can find that out as well. So when there is, you know, you have variation from 0, 20, 40, 60, 80, 100. We are looking all the time at the same problem. So let's look at the energy which is lost. You know, so when it is 35, then, you know, that energy is lost. When the peak load is 35, peak load is 45, when peak load is 55, 65, and 75. The entire load is lost because generated capacity is only 0. So 35 lasts for 5%, 45 lasts for 15%, 55 lasts for 30%, 65 lasts for 30%, and 75 lasts for 20% of the time. So that's, you multiply and you get 59.5. Likewise, when you come to 20, so when you have a peak load of 35, then you would lose, you know, if the peak load is less than 20, you lose nothing. But if the peak load is 35, for example, then you lose 15, which lasts for 15% of the time. Then the peak load, you know, that profile was given, how long the 35, 45, 55, 65, and 75 lasts. So if 35, the peak load is there, so it lasts for 5% of the time. So you lose 15 megawatt for 5% of the time. Then if it is 45, then you are in a state of 20 megawatt. So your generated capacity is only 20. So you lose 25 megawatt here. You lose 35 megawatt here, lose 45 megawatt, and you lose 55 megawatt for this percentage of time. So that's 39.5. Then when your capacity is 40, then you don't lose 35, but you lose when you have 45. So you lose, when you lose 5 megawatts here, you lose 15 megawatt here, you lose 25 megawatt, you lose 35 megawatts, and these are the percentage of time they remain same. That's not a big deal. Okay, so that's 19.75. When you are in state 60, you'll not lose 45 and 55 megawatt states of the load, but you'll lose when the load is 65 and 75, these loads. So 65 means you lose 5 megawatts. 75 means you lose 15 megawatts because you are in state of 60. So, and this happens 30% of the time, this happens 20, so you lose 4.5 cumulative energy loss. When you are in 80, because the peak is anyway 75, maximum it can be 75, so you lose nothing. When you are in 100, you lose nothing. So these are the various possibilities. So what do? Total energy which is supposed to be supplied when there is zero capacity. So this gives you the total energy to be supplied is 59.5. Total energy lost, you know, when these possibilities of various peak loads are there. So we sum up all these three. Sum these, why these three, when zero is also there. So you sum up these four, 59.5 as well. And the probability of being in state zero is a number of zeros, 5 zeros and 256. So 59.5 when the state is zero, and the probability is so low. Likewise, 39.5 when you are in state 20, and the probability we have calculated for state 20, and probability we have calculated for when the state is 40 megawatt. Probability we have also calculated when the state is 60 megawatt. So the total energy lost is so much, and then total energy is supposed to be supplied. So loss of energy expectation is you divide the total energy requirement and the total energy lost. So this is kind of fraction of the total energy which is lost. So this is what is lost. And therefore the energy index of reliability is 1 minus loss of energy expectation. So the energy index of reliability in terms of the energy which is made available and the energy which is lost. So that's 0.995375242. I think, Professor Vivek, can we close today?
Yes, sir. We can, sir.
Okay. So we can close today and we begin tomorrow.
Sir, there is some queries in the participants. Mr. Ankush, Vishwanath K and Raman Bhatt. You can ask Mr. Naman, Ankush. I don't think so. They are here now.
Yeah.
Sir, I have a question. Can I ask now? Tomorrow I'll discuss.
Yeah,
You can ask, no problem.
So exactly that FMEA, how we can make FMEA in holistically for a machine?
Failure mode effects analysis.
Yes, sir. Yes, sir. Because suppose I'm in industry, so for a machine, suppose a rolling mill, we are aluminum rolling mill.
Yeah.
So for making an FMEA in a machine, so what is the approach? How we make a FMEA successful? And that is my question, sir.
Yeah. So basically, one thing is that we should know that it's a bottom-up approach. Unlike fault tree analysis, which is a top-down approach, this is a bottom-up approach. And then we are looking at the functional failures of components, subsystems, components, units, subsystem, and system. And what is the impact that components and units and subsystem would have on the system failure? And what is their criticality? You know, the criticality ranking is possible. And if you know what is the impact on the system failure, then you can try to make the design, you can try to make the system more robust by initiating some corrective or preventive measure in trying to either provide redundancy or to provide more components or parts which can withstand greater stress, or by trying to use some derated parts and units so that it doesn't fail. So the important thing is to identify criticality and the impact of the failures of units, components, subsystems on the system, and therefore the criticality. So you do a criticality ranking, and then why do you want to do a criticality ranking? Because you want to initiate measures to make the system more robust. You want to make the system more reliable so that it doesn't fail. So you want to find out functionally. First, you have to basically relate these components, units, subsystems to the system, and then define their functions, then find out the role and their criticality in bringing about a system level failure, and then initiate corrective and preventive measures by which you can make the system more robust. I mean, at least that's the way that I think from an industrial perspective point of view.
Sir, my question is that how you implement, suppose in an organization, suppose somebody, some electrical background and some mechanical background for implementation of holistically. So what is the approach? That is the thing. Suppose it's a single man can be possible or a cross-functional team. for making an FMEA?
It is a teamwork in which you need to involve the design people, you need to involve the operations, and you also need to factor in the experience of the maintenance crew. So they'll tell you what failures can happen and what are they primarily due to. So you define the function of the system, and then based on the systemic function, which is essentially required for the system to for which the system is meant to, then you find out what are the critical subsystems. Is it the power supply system? Is it the control system, for example, or is it the some driving mechanism is there? So functionally, first you need to relate to the total function of the system, and then find in terms of criticality or ranking which of these sub functions can either occur in terms of frequency or in terms of importance, which can prevent the system from operating continuously and bringing about a failure. So then you go down further to those subsystems, units, and components. So at the end of it, you identify various units which are critical to it, and therefore what can be done, what measures can be initiated to prevent system failures from happening, and the impact that these failures at the lowest level can have at the level of system.
Okay,
There is
sir. Thank you. That
a US military standard which is 1629A. So I think if you happen to go through it, it will tell you how to conduct this failure mode effects analysis. And of course, there are many other standards also which also tell you that. But since most of this approach has basically originated from the US Department of Defense, so they have military handbooks and standards. So 1629A refers to the failure mode effects analysis.
Sir, is it available, that book? That is a book or some document?
I think, I mean, like older versions, because they keep having meetings and they keep revising it. So there'll be older versions which are probably available. Of course, they would like to price it, but anything today you want is in some sense available on the internet. So you can search for it, and I'm sure older versions will be available. So newer versions may have a few more explanations, a few more additions, and few more examples, nothing much. So even earlier version will help you to understand and make carry out this analysis.
Thank you, sir. Sir, all these PDF are available to us now after this successful training, because there's so many things, remembering all these things and some exercise for reference. We require.
Yeah, of course. The slides will be made available to you subsequently when the class gets over. And I have also listed out the main reference. There are too many references, but I thought it's pointless to give you too many references. Just one or two books which you can read, because as it is, we find so little time to do, amongst everything else, you want to study something new. So it's better to study a few good books rather than too many books. So you can read up these. Roy Billington book is very good. One book is on the reliability evaluation, and another is on the calculation, and then there are hundreds of papers. So you read up these two books; they are very good. And that Casey Oglu or Patrick Connor book, they are very good. And there are so many other books also on reliability.
Sir, I just want to add, Today I have already shared the handbook of Dimitri and the reliability calculation by Roy Blinton with all participants.
Yeah, that's great. That's great. So that has almost everything. There is nothing which is left out. Actually, all the stuff that anybody in the world teaches on power system reliability, if he is not referring to Roy Billington, then then he's not probably he's being unfair and is not doing justice to this course. So I had a great fortune of having edited 2 books along with Professor Roy Billington, and therefore you can say some reason why I'm also very fond of him. So that was a great opportunity. And so I would say I would always refer to his books. They are the best probably books. Of course, I haven't taught this course for years together, and it is only on some occasions I have taught this course earlier because of but because of some close association I had for some time with Professor Roy Billington, that I really got deeply interested in this subject, and I wanted to understand the nuts and bolts and the nitty-gritty of it, and I found it really very interesting, and therefore I would like to refer this book to everybody. I would personally I have my own personal copies. It is available on the internet, but that's all right. If you are in a hurry and you don't have that book available, probably you can refer to some things here and there from the net. But I would personally advise that all of you who are seriously interested in this subject to get your own personal copies. To get your personal copies of the book. The pleasure that you get in reading, these hardbound copies is immense, and it cannot be offset by any any pleasure that you may derive from reading of whatever is available on the internet. So I would personally urge everyone to get a copy of the book. So all the textbooks that you find have been very well written. They have invested so much of energy, time, and experience, and therefore, I think this is a very little tribute that we want to work in that area. We are interested in that, and we hesitate, to buy copies of that book when they are not even priced very high. So I would urge and request everybody to try and get a copy of Professor Roy Billington's book, which is so well written, with a lot of experience and enthusiasm and interest.
Thank you, sir. Thank you for your insight. Thank you very much. Good night. Thank you, sir.
Okay, sir. Thank you very much, sir.
Thank you, Vivek ji.
Participants,